So today is the last day. Hope you all had a good sleep, you're energized, and we will talk a lot about irritability again. Okay, we'll talk about two topics today. We'll recap what we talked last time about memorization and finish the proof. And actually we'll give a solid proof that edge coloring is not a H card. Then we'll move to much more obscure topic, to proofs of bioarithmetization. We will show that a lot of problems have. So I was at the beginning saying that like I'm using the word implausible a lot, that like some reduction is implausible. So what we'll be talking in the second section is even this word is too strong for this. There is a barrier to creating a reduction, right? Okay, so let's go through what we talked last time. So all the reductions all the non-reductions are going down, except the kind of like stupid ones, which we artificially created specifically to show upwards reductions. So all the natural reductions, in the realm of like natural problems or like reasonable problems, they all go down, and we don't know if it's like some kind of law of nature or we just can't find them because I don't know why. We have this problem edge coloring, which we believe is not solvable, which we don't know how to solve faster than 2 to the O of n square, which is amazing because it is 2 to the s, where s is the size of the description of the instance. Right? So one of the big questions is it an H card problem? Like, is it a reduction that proves that you cannot solve it in 2 to the little of n square? And we have some partial results about that. So, okay, what if we'll try to be like even more ambitious? So, what are the best possible results about hardness of edge coloring? Well, we find a reduction from strong ETH that proves 2 to the alpha n square lower bound. Right? So that would be really okay. And we can answer that such reduction doesn't exist in some sense. All right? And I think we stopped here last time, right? Okay, any questions about any of this? Okay. So let's go then. So, yeah, this is a theorem that we'll try to prove right now, that edge coloring 2 to the cn square is, if it's SSH card, then SSH fails. Which, again, means that there is no reduction in a meaningful way. So, what we need from edge coloring is only that it's a hard problem. That the second parameter is 2 to the cs, where s is the size of the description. Right, we talked briefly that like you need n square bits to describe graph, right? That's why 2 to the n square is 2 to the s. Alright? So if you'll find any problem that with this property, then SSH fails.
This is for c smaller than 1, I mean.
For any c. Like, for any c, well, for any c greater than 0, yes.
But haven't you said that you actually can solve it in 2 to n square?
Yes, we can solve it in 2 to the n square. Yes.
Which is 2 to s.
Yes, but
2 to 1 times s.
Yes, but maybe there is like a better algorithm. So we probably can, like, we're talking about undirected graph, right? So there are at most n square over 2 edges. So you can solve roughly, right? So we can solve it actually in 2 to the n square over 2 already. So maybe if you try to optimize, you will get another constant factor. That's totally plausible, right? I don't think anyone actually looked into improving this algorithm in terms of constant and front of n square. At least I haven't seen such results. But maybe, so probably, but like, you expect that there is some constant. That's at least my intuition, that we don't know how to solve it in 2 to the little of n square, so there should be some constant such that the optimal running time is 2 to the alpha n square. And the question is like, can we prove, for, at least for some c, that this lower bound under SSH? So maybe not the optimal, can we prove some lower bound?
So can you say what does it mean that a comma 2 to s is SCTH hard in that case? Or
so there is a reduction that proves that a is 2 to the cs hard. Okay.
Could you explain this theory?
No, we haven't.
I mean, the statement.
The statement, so okay, we have, so yeah, if for some problem, so C is the size of the instance in terms of number of bits, right?
Okay.
Yes, and C is just any constant, any positive constant.
Okay.
So if you can prove for, and suppose we have this problem, this find random statement A to the CS, if it's, you can prove that it's SSH hard, then SSH fails.
Okay.
Right?
For arbitrary problem A.
Sorry? For arbitrary problem A, yes. So, one of the natural examples is edge coloring, the other would be edge click cover. And I think there were a couple variants of problems that deal with edges generally that we don't know how to solve faster than 2 to the n square. All right, so again we need to take a look at the fine grained reductions. So what we'll try to do is to speed up. So we'll just take the reduction and we'll try to speed it up. That's it. And by this we'll convert it as a SSH. So we will. I've talked briefly last time that we will try to use memorization. So whenever you're trying to do an oracle call, you check if you already was recording an oracle on this instance. So we'll try to simulate the same. So as before, we'll take a reduction and we'll try to simulate it without an oracle. So if there is, if it's the first time we encounter this instance of problem A, oh, it should be 2 different problems, S, SAT, and A. So this should be SAT, right? So whenever we encounter a fresh instance, we just solve it in some brute force algorithm. So some reasonably good algorithm. And if we already seen this instance, we'll just output the same answer, right? The question, will it always give us some good results? Well, hell no. Like, why would you expect that these techniques will give you anything good? Because, for example, the reduction can just make one call, right? It can be just a hard reduction. In this case, memorization will give you no speed up at all. It will never do anything useful. All right. So how can we get around it? How can we make our reduction do a lot of calls? So we will benefit from the reduction making a lot of calls rather than just one. How can we force it? Any ideas?
Maybe you should try to solve many instances of that.
Yes, but okay.
And then show somehow that solving many instances, independent instances of SAT is hard.
Yes, that is exactly what we're going to do. We will reduce SAT to many instances of SAT, and then we will run a reduction on each of them. So, and that brings us to the notion of self-reducibility. So, we start with SAT, and we can, if I give you an algorithm that works on instances of size alpha n, that is faster than exponential than to the n. So if I can solve instances of size alpha n faster than 2 to the alpha n, I can solve instances of size n faster than 2 to the n. Any ideas how to do that?
Just
That's the right word. Just branch on 1 minus alpha n variables.
So there's 2 to alpha n in this first
Sorry?
exponent.
First exponent.
Oh yeah, that should be so sorry about that. 2 to the alpha n, yes. So we branch on the first alpha 1 minus alpha n variables. We're creating 2 to the 1 minus alpha n instances, and then we solve each of them faster than 2 to the alpha n, which gives you better than 2 to the n algorithm at all. Okay, and in fact, this will be the only property we will use from SAT, which means that you actually cannot prove that edge coloring is hard, not under just SAT, but under set cover conjecture, or under Hamiltonian cycle conjecture, or under orthogonal vectors, or whatever other problem that has this property of efficient self-reducibility. Right? Okay. So what it gives us? We have a SAT problem, instance of SAT, which we hit with a self-reducibility, which in SAT is just bunch of variables. Then we have a lot of reductions. Then we have a lot of instances, and we apply our reductions to each of them. And then our hope is that now our reductions make sufficiently many calls that memorizations will start to kick in and speed the whole process up. Right? Does that sounds intuitively okay? Okay. So yeah, basically we only need that the problem we're trying to reduce from, it has efficient self-reducibility, and the problem we're reducing to is exponentially high. So what we need from find domain reduction? So we were saying that there is a reduction from SAT to edge coloring that maps 2 to the n to 2 to the CS, right? So what can we say about incisors of the instances that Oracle is calling? So the sizes of SAT instances after self-reducibility are alpha n. But I'm interested in the sizes of edge coloring instances that we are making Oracle calls to.
Alpha n.
Oh?
Alpha is going to be there also.
Yes, but there will be some other term, right?
So they can be different.
So yes, they can be different, but they will be all up to size. They will be all up to sized. So if we have a reduction from SAT to the n to a to the CS, right? Then the sizes of these Oracle calls, will be less than what? No, that would be running time. So what would be the sizes of the calls?
Alpha n over c.
Yes, alpha n over c. That is correct. Right? Okay.
could you explain what you were counting?
So we are trying to estimate the sizes of those instances. So after we branched on almost all but alpha n variables, and we applied our reduction, each instance we are calling of each instance of A we are calling has size at most alpha n over c.
Why
Because of the reduction. So suppose the size was more than to the alpha n over c. Well, then this fine grain reduction is incorrect, right? Everybody on board? No. So the question is why we have C here?
Yes, we substitute 1 minus alpha n variable.
Yes, we
We
got,
get set of size alpha n.
yes.
What is going on later?
And then we apply our reduction.
Okay.
And our reduction was mapping complexity 2 to the n to complexity 2 to the cs.
Okay.
So if the size was more than that, then reduction is incorrect. Because, well, well, we can prove it formally, right? Suppose we have our reduction was making a call to something more than this, right? Let's say alpha over c plus epsilon times n. Okay. I am applying the definition of fine point complexity, and I'm telling you that I am giving you an algorithm that is faster than 2 to the cs by some constant. Actually, let me plus that. So, suppose I can solve instances of a in 2 to the cs minus so suppose I can solve a in time all right. Well, then I will be solving this instance in this amount of time, right? So if my epsilon is less than beta, then this whole thing is more than 2 to the alpha n, which means that the whole sub will be slower than 2 to the n, which is like opposite of what we wanted, opposite of what fine-grained reduction was supposed to do, which is a contradiction because we assume that we are given a fine-grained reduction. All right. So all the sizes are ignored this, which is pretty nice because how many of those we have? Well, so there are at most a number of different instances. Is at most, well, it's 2 to the right? So, and I will want to solve a on each of them. And for h column, I know how to do it in 2 to the s. Right? So I can solve a on all instances of size less than alpha n over c in time. Oh, this is actually we don't need. So we can solve on all of them in what? In 2 to the alpha n over c squared. So because we will have at most 2 to the alpha n over c of them, and to solve each of them we need 2 to the s, which is again 2 to the alpha n over c. So, and this square goes. Fantastic. But at this point we should realize that, well, we haven't picked alpha yet. Well, we just need to make alpha, to take alpha such that this expression is just less than 1. That this whole thing is less than 2 to the n.
Sorry.
Yes.
We have an instance of size alpha n over c, and so you mean you apply the algorithm just.
I will just solve. I will just brutally solve all the possible instances of A.
You mean so you are assuming that there is an algorithm?
Yes. I don't need to assume that there is an algorithm. Yes.
Okay.
Let's solve it in 2 to the s. Yes.
Mhm.
All right. Yes, and at this point we pick alpha to be in a way that this is less than 2 to the n. And it means that we can fill our table sufficiently faster than 2 to the n. Right? But after we fill the table, we have a constant time algorithm for A. Right? Which means that fine-grained reduction should give us something better than 2 to the alpha n for the small instances, which means that we have something better than 2 to the n for the original instance. We should refute this stage. And we're done. So there are nothing more on the coverage. That's it. So our algorithm would be to first fill the table for all possible instances of A. Then we'll start with so then our reductions. Then we will have a constant time algorithm for A. Just check the answer in the table. Just look it up. Right? Then by definition of fine-grained reduction, we will have faster than 2 to the alpha n.
Are we filling them for all possible inputs or for those that we really require?
So at this point, it actually doesn't really matter, right? So we can be like we can optimize and only call it for instances we actually care about, but it's either.
I just mean we can't choose only those we care about at the beginning.
No, we cannot, but we can. So it's a little bit harder to analyze. I mean, it's roughly the same, but it's a little bit harder to say it's formally that when you can fill the table on the fly, right? And then you will have time complexity less than 2 to the n. Instead, we can first fill up the table with every possible instance, and then our reductions will run faster than 2 to the alpha n, which means that the whole algorithm will run faster than 2 to the n.
Why do you know that 2 alpha divided by c is smaller than 1?
Because we can pick alpha.
Okay.
We will just pick alpha to be less than CO2.
We can pick alpha.
Yes. Alpha is just a percentage of variables I'm not branching on,
okay.
right? So C is some given us constant, but alpha is we have full control over.
Sorry. And does it immediately apply? So if you have an algorithm for edge column, then when C is not constant, but you have an algorithm which is slightly better than to the end for some.
Yeah. So if C is not constant, everything falls apart because number of possible instances is now too large. So here we highly deduced that it's a very hard problem, which means that instances are very small, which means that number of possible instances of the size is actually really small. When we go below exponential time, this is all technique is no problem. So we'll have problems with this term.
So the solve, it means oracle false.
Sorry?
Solve all means oracle false.
So yeah, we can either have absolutely all different instances, or we can be like smart and solve only those that we.
We use emergence.
Sorry?
We after all need to merge this.
Merge? No. We will just have a table with correct answers for every single possible oracle call.
Okay.
All right. So, how much time do we have?
No.
So, okay. Let's just give the conclusion that yes, edge coloring to the CN square is not as if it's a SSH hard, then SSH fails, and SSH can be replaced with a lot of other conjunctures. Okay. So let's go to our next topic. Yes.
Is it only use of memorization of it as a barrier, or there were some other instances?
Sorry?
Is it only an example in which memorization is used as barrier, or it is a common way of using memorization of a barrier?
So I don't think it was used in this way before. It's just, I mean, it's kind of natural, right? If you have if you're calling the subroutine like a lot, then well, you expect memorization to work. So it's just that, yeah, its memorization as a better is a fancy word. It just means that, yeah, such reductions are really, they really shouldn't exist, more or less. Okay, so let's talk about something else then. Yes.
Which features of problem A were used here?
Only that it's hard and that the targeting time complexity and the upper bound we have already are pretty close.
And that's it.
That's it. Yes.
So are there any similar problems with such problems?
Yeah, like H-clip cover, for example, or I mean, there are like all these problems on compressed instances. Like I'm giving you a circuit that types a problem that you actually need to solve, but they're like kind of unnatural. So the question is that I'm going to ask is that what we did basically, we created a lookup table for all our Oracle calls, and lookup table is like not the most impressive computational device. So the question is, can we, instead of like just memorizing all the instances, try to be like smarter about it? And that is exactly what we will try to do this, and we will call this technique arithmetization. And yes, we will try to put small circuits instead of memory table. All right? So, what is the general strategy of the results we will try to prove right now? We will start with cell reduction of subs. So, we'll try to mimic this picture as hard as possible. We'll first hit some instance with self-reduction. Then we guess and verify a small circuit that solves instances of problem A. Then we run the reductions as before, and we use the small circuit that we guessed for the second stage to insert the oracle, and this whole thing refutes an stage. So we are back to non-deterministic world. I'm using again the standard deterministic fine-grained reductions to create a faster non-deterministic algorithm. Why do I need the non-determinism? Well, that's this nasty word guess, right? So I will construct small circuits is really hard. So what we'll do, we'll just try to guess the circuit.
And sorry, can you say what are you trying to improve in this?
Oh, so we want to say that about a lot of different other problems. So we are done with edge coloring, but we want to talk about other problems now. And the problems with other problems that they are not that. So about problems with not exponential time complexity.
So for problems not of this type.
Yes. So we don't have. So if we don't have this upper bound in size, then we cannot use memorization. So we need some smaller device than some table. And what is the smallest devices? Yeah, we will try to come up with a circuit. All right.
How do you verify the circuit?
Oh, we will get to this point. This is tricky, yes, because usually you can't verify a circuit in a reasonable time.
And in order to guess, we should guess, if we guess something non-deterministically, it is usually assumed that we can check it, or not.
We will have to check, yes. So we will use some properties of the problem for which we are guessing the circuit to speed up the verification. So we will not guess any circuit, but a circuit that has specific properties which will allow us to verify it much faster. No, but in a small exponential time. Okay. So let me introduce you to polynomial formulations. This is our bread and butter for the next 1.5 hours. So let's dig in. It's unnecessarily complicated, but that's what we have. So a problem A has so polynomial formulation is a measure of complexity of a problem. All right? So we're saying that problem A has polynomial formulation of size S. If there is a reduction from A to evaluating of
Polynomial is independent of the reduction. There is a polynomial for
there is yes, there is so yes, I think I actually have it. Yes, so it means that for all instances of the same size we have a same polynomial, and this should be like a simple polynomial, which means that we can compute its coefficients in a very small time, in any reasonable time. Alright? It's like what in arithmetic complexity is called explicit polynomials. Is this definition clear? This is very important. Alright. So here's the theorem we will tackle today. So suppose we have a SATH problem like AT that has a polynomial formulation t to the alpha for all positive alphas.
So your first fixed polynomial, so when it's known how many variables it has, yes?
Yes.
So how,
So
when you apply it to different t?
so for each size of polynomial formulation, I will have different polynomials. So depends. My polynomial will depend on alpha, right? And the degree will depend on alpha. What will be still constant. Because we have this condition that polynomial should be of constant degree, there is no such thing as a minimal polynomial formulation. We have like a minimal polynomial formulation with a fixed degree, but as we allow degree to grow, there is an infinite, but there is no minimal. So what we just have is the existence of the sequence of polynomial formulations of a smaller and smaller size. So, but each of them has a constant degree. Right? So if you found such a problem, then one of two cool things happens. Either NSTH is wrong, well, or permanent is not computable by non-commutative arithmetic circumstantial expansion sets. And if you have no idea what it is, that's totally fine, but it's something people were trying to prove for decades. And right now the lower bound we have is n log n, I guess. So there is a gap. There is a gap there. All right. So the very natural question you should be asking right now is, well, why should I care? So this is some super artificial measure that no one cared to state before because, well, it sounds really, really weird. So, but fortunately, this property of having small polynomial formulation is true for a lot of natural problems. For a lot of problems on graphs, we can design polynomial formulations, and it's not actually that hard. So independent set, independent cycle graph coloring, and set cover, all of those problems have small polynomial formulations. All right? Any questions so far?
Why is this problem doesn't match Saint-Petersburg argument about memorization?
Oh, they are not hard enough. They are not two to the s hard. For example, commutative cycle is a problem in a graph, right? Graph is defined by n square bits, which means that it's 2 to the square root s hard, right? Or like, yeah. For independent set, you can reduce to sparse graphs, but even graphs of constant degree require require n log n bits to describe them. So again, it's 2 to the s over log s hard problem, so memorization is not going to give us any juice. Right? But yeah, that's actually basically the statement of what we're going to do in the problem session. That will come in how many minutes?
20.
16, okay.
Which is 6.
And if we'll combine everything together, we get this. So this is a very, very representation that all of those like supernatural problems to which we would love to have SSH reduction. Well, it would be hard. It's not saying anything about non-existence of such a reduction. Why? Because we believe that second statement is true. So we actually believe in the second statement. It's not a weird contradiction, but proving that should be really hard. Should involve some really good new ideas. Yes.
Does it mean this? For example, independent set. So if we have a polynomial formulation for c to the n for every c greater than 1, then
Yes.
it is unlikely that we have for any constant fine-grained reduction from sat to 2 to the alpha n
Yes.
time for independent sets.
Yes. So we can prove any lower bound. Not just a correct lower bound, but like any lower bound. And actually, right now I want to say one more like a philosophical feature of this of the thing is that this is talking about proofs by reduction a lot, because we know that independent set requires c to the n under SSH. And it doesn't contradict this, because there are two different phrases you can say. Independent set requires c to the n if SSH is true, is one statement, and independent set is SSH hard for c to the n. What is the difference? The difference is that second statement requires to give a reduction, while the first statement is just a logical implication. So why SSH implies that independent set requires c to the n for some c? Who knows?
Because STH plus ETH.
Yes, exactly. SSH implies ETH. We don't know. So, and ETH means that there is a constant such that ETH is 3 sat is not solvable faster than c to the n. And there is a fine-grained reduction from 3 sat to independent set, which we should convert this constant to another constant, right? So under the fact that SSH is true, we actually have those lower bounds that we claim we cannot prove. So this is very important that we are saying that we cannot prove them by reductions. So while this c to the n lower bound exists under SSH, the pinpoint the exact c would be extremely hard. All right? Okay, question? Yes.
And there should be or between slash two
Yes,
words.
yes, one of those, yes, exactly. So, you might be concerned about the second, that we have OR of two statements, because proving OR of two amazing statements is really easy. Let me give you an OR of two great theorem. And P is equivalent P, or and P is not equivalent P. Both statements are extremely impressive. So you taking OR of them doesn't give a great statement, right? So it's not closed under this operation greatness, all right? But I'm claiming that those two statements are roughly of the same flavor. So, and in this case, it's kind of okay to do that. So if NCTH is wrong, give us circuit lower bounds. Yes.
So you said that the problem is to pinpoint the actual constant. So what about if there is some, I don't know, hypothetical reduction from SATH that would not be the classic reduction, but would say that there is some range of constants. Actually, we know that, but there is, that if you, right?
Yes, that will be totally, yes, that is fine. But you need to come up with some sensible definition of such reductions. And in that case, yes, we cannot rule those out, yes. All right. Okay, I have 10 more minutes, right? And then let's talk about why. Like, I will not be able to give you the whole proof, right? But we can try to make some sense of what is happening. So, why we need polynomial formulations in the first place? Why we need this definition? Let me go back to the definition. So, why do we care that it's a constant degree polynomials? Why do we care that they have? So we will need that they have small exponential number of variables and a constant degree. So why is this useful? Because I will try to guess an arithmetic circuit that computes this polynomial. Alright? So what is cool about arithmetic circuits for constant degree polynomials? If there exists an arithmetic circuit for constant degree polynomials, there is a homogeneous arithmetic circuit for this polynomial of roughly the same size. And I have just 10 minutes, so if you don't know the definition of those words, I guess that there is nothing I can do.
But polynomials should be homogeneous.
Yes. Yes, we can always do that, right? Okay. So if there is a small arithmetic circuit for the computed polynomial of constant degree, there is a small homogeneous circuit of the computed polynomial. It means that at every gate we compute a homogeneous polynomial, right? But then you can and then we deal exactly with the concern that guessing a circuit it should be easy, but verifying is the hard part, right? And we will actually attack this problem during the problem solving session, that verifying a constant degree polynomial computed by a homogeneous circuit is actually not hard. I mean, it's exponentially hard. It's, well, polynomial in the number of variables. Number of variables we have here is exponential. So we'll deal with that in exponential time. And again, because of this picture, exponential time would be not a problem, because we will hit our sub instance with self-reduction before to bring all the so in our algorithm we will have some number of exponential time terms, but by hitting this with self-reduction we will bring all those terms below 2 to the n. And this is the general idea. So in the problem solving we'll do 2 things. We'll see how to guess and verify arithmetic circuits, and we will prove polynomial formulations for all those natural problems. All right, I think it's time to stop. Yay!